he was my co-advisor. I learned so much from him, and it's a huge coincidence to have him as our first keynote, so I can introduce him. And I think everybody knows how great he is, how many research projects he has. He works in analog, he works in and now this new topic, so towards designing and deploying IC machines. I'm so excited to see this topic, a new topic for me. So I hope everybody enjoys. Yeah, welcome.
Thank you. It's great to be back at ICE indeed, and it's wonderful to see this rich and diverse community. It's as vibrant as it was about 20 years ago when I was first involved in this. So today my talk is going to have something that superficially has nothing to do with physical design. There's no placement, there's no routing algorithm in here, etc. But you'll see as I present this that everything that's done here actually has its roots in skills learned at ISPD. There are some partitioning issues, there are some physical design issues that are sort of hidden in the back. And in general, there's sort of a big picture issue. How many of you know what an e-sync machine is? Raise your hands. Okay, so I was in your position about 5 years ago. I didn't know that either. And so I'm going to start with a very basic presentation and kind of take you to the details of this. So I'll first talk about the concept, and I'm going to use a video from YouTube to illustrate this. Now, superficially, it might look that the video has absolutely nothing to do with physical design or chip design or anything of that sort, but let's just take a look. It's a bunch of metronomes. If any of you have kids who play the piano, you know that a metronome or violin or something like that is something that keeps time. And it's basically a very simple mechanical oscillator. So in this picture, there are 5 metronomes that are placed on a platform, and they're all running at the same period, but they're all independent. So the phase difference is kind of completely sort of whatever it is. Each one has nothing to do with anything else. Now the thing that changes, as you'll see, is that this guy puts the platform on a couple of cans of soda, and you'll see something change over there. Notice that the cans are actually beginning to roll around a little, and over time, the oscillators all synchronize. They're now all working in lockstep. This is actually a fairly well-known phenomenon. This is known as injection locking. This has been around for a while. And in fact, it's not even kind of new in any sense, because there's this picture from Huygens from 1673, where Huygens, if you know, had a number of contributions to physics, including diffraction patterns, etc. But one of the things that he did very well was building clocks, and these were pendulum-based clocks. So he had these couple of pendulums that were suspended on a platform that's shown over here. And what he found was that when he left them suspended, these were supposedly independent clocks, and as you can see, there are also 2 oscillators. After about half an hour, he found that they were actually completely 180 degrees out of phase. So it was basically going this way, this way, this way, and it was too much of a coincidence. He first thought maybe this has something to do with air movements, but it was too consistent to be that. Well, there was actually a theory that he explained, and one of the sort of mysteries was why they were out of phase instead of being in phase. And there's this paper from 2017 that analyzes it, and the short answer is that they're out of phase because the mechanism with which they were suspended on the platform had something that promoted being out of phase instead of being in phase. But basically, there is some interaction between these supposedly independent things. It's a nonlinear interaction through this medium that allows injection locking. Okay, so that's the first part of the story. And at this point, you're probably thinking, well, this is sort of a nice, interesting thing to learn. What does this have to do with computation? Well, if you think about this, there's a notion of phase over here. So you can have oscillators that are in phase or out of phase, and you can think of the state as being the phase of the oscillator. And now you can think about this being something like a digital system in that sense. Okay? Now, let's also kind of look at this. We can use it to solve optimization problems. I show you a very simple optimization problem, number partitioning. The idea is that you're given a set of numbers. I've got these 6 numbers shown over here, and I want to put them into 2 true so that the sum is roughly the same. So I try this and I find that the greens add up to 17, the reds add up to 33. So I try again. Now it's an uneven partition. You all know about partitioning. It's 22 and 28, a little closer. And if I play around a little more, I get a perfectly even partition of 25 and 25. Okay. Now, this is a fairly simple thing to formulate as a mathematical optimization problem using something like 0, 1 ILP. So we assign variables over here, except instead of 0, 1, we'll assign them to be minus 1 and plus 1. And for each of these numbers that I have, the 6 numbers, I'm going to assign a variable called SI. And the SI can take a value of plus or minus 1. And I'm going to minimize this quadratic, which is SI times NI squared. Okay, what does this do? If SI is minus 1, then all of those are going to be subtracted. If SI is plus 1, all of them are going to be added. So my green partition, for example, could be minus 1, my red partition could be plus 1. If they are balanced, this is going to be 0, and the minimum is going to be when this is 0. Or if it can't be exactly balanced, it's as close to balanced as possible. So I can write an optimization problem of this sort, quadratic optimization. We've seen this, analytical placement, etc. You're all experts in this thing. But the catch here is that this is not continuous. This is minus 1 or plus 1. It's a discrete space. Now, if I expand this out, when I expand this, I get an S1 squared, S2 squared, etc. And those all turn out to be 1 because each SI is plus or minus 1. So because it's constant, I can toss it out of the equation. So what I'm left with is a minimization of all the SI, SJ terms, and it looks something like this. Okay. Now, notice again, as you know from placement, whenever you have a quadratic, you need some kind of a reference point, otherwise you might get a trivial solution. In this case, the trivial solution is my left partition could be minus 1 and my right partition could be plus 1, or vice versa. Okay? So in order to provide a reference, I can set one state, for example, S1 to be minus 1, and then I get a quadratic of this sort to minimize, and now since this number is in minus 1, I'm going to get a solution which concretely puts numbers into one partition or another. Okay. So what does this have to do with metronomes? Well, I can actually take these minus 1s and plus 1s and assign them to the state of the metronome. So I can think of the phase of the metronome based on the reference phase. This could be the minus 1 phase, this could be the plus 1 phase. It's either in phase, which is 0 degrees, or out of phase, which is 180 degrees. And then I can connect up these metronomes using these weights, and these weights are the KIJs, and that's the strength of the connection between oscillator I and oscillator J. And then I can basically just wait for nature to take its course, because nature favors low energy states, and it's going to settle into a natural minimum. And that's basically what happened with Huygens, that's what happened with the soda cans, etc. And so you eventually get the result that you expect to get, which looks something like this, except that I set this as the reference state. Okay. Now, we used a metronome over here. It's a pretty lousy oscillator. Well, it's great if you're playing music, but it's pretty lousy in terms of doing electronic computation. Fortunately, there are many other oscillators that are available in the electronic world. So there are metronomes, of course. There are superconducting oscillators. These are actually used in this context. There's a company called D-Wave in Canada that you may have heard of, which uses superconducting Josephson junction-based oscillators to solve problems that are very similar to this. You can have optical oscillators, you can have spintronic oscillators, so this is governed by something known as the LLG, Langdon-Lifshitz-Gilbert equation, which tells you how the oscillation proceeds, and you can couple oscillators in that. You can have phase change oscillators based on vanadium dioxide, etc. And then coming back to our world, you can have the Humboldt-Steam oscillator, which is a so-called dirty oscillator, but it actually is something that you can couple fairly easily. And unlike some of these things, you can actually build it at TSMC or Global Foundries or wherever, and you can operate it at room temperature instead of working at 20 millikelvins. So how does this work out? So we have these coupled oscillators. Initially, they were metronomes. Now we're going to use ring oscillators. And ring oscillators, as you probably know, are basically just a bunch of inverters connected in a cycle with an odd number of inverters, and it's going to cycle forever. Okay. How do I choose coupling between these? If I want a coupling, I can take, say, this ring oscillator and this ring oscillator and connect them with a resistor. So what does this do? It basically says, if I have the reference phase for each oscillator over here, this is going to try and make sure that this voltage is close to this voltage, and it's going to try and couple them to make them in phase. I can also make them 180 degrees out of phase. I can have negative coupling by connecting this with something that's 180 degrees out of phase and promote these to be coupled, which means that these will be 180 out of phase over here, and therefore the reference will be 180 out of phase. How does this work? Let's look at net A and net B as shown here. So the dotted lines, which you can barely see here, are the clock waveforms if you didn't have any coupling. Now let's say at time 0, you insert this coupling over here. What's going to happen? At this point, this is trying to rise, but as A is rising, B is low. Right? So what's going to happen is this is trying to rise, but this is low, so it's actually fighting that rise over here, which means it's going to slow down the transition. So instead of making the transition at this dotted line, it's just a little to the right over here. When it comes over here, this is trying to fall, but this is high. So as it's trying to fall, it's being opposed by this, so it moves a little to the right. Again, it moves a little to the right on the next phase, etc. And progressively, as you go here, this moves to the right a little. The phase actually gets delayed. If I look at the effect on B, when this is low, this is trying to rise. This is already high. So if this is trying to rise and this is high, this is actually helping the rise. So it's going to speed up the rise and make it come a little earlier. And eventually, as this goes down and this speeds up, they're actually eventually going to lock into phase over here. Right? So that's the notion of how you can use ring oscillators to create coupling and get things to work. And that basically gets you to building coupled oscillators using electronic components, which can operate at nanoseconds or microseconds at worst if you use something really bad, as opposed to seconds for a mechanical oscillator. The advantage of this, like I said, over doing something with something more fancy, this is a model that's known as quantum annealing. This is being done at millikelvins, which means that you need expensive refrigerators, you need expensive components, you need cryo CMOS to control all of this. As opposed to that, this is a chip that we built. We, as in my colleague Chris Kim, is actually the mastermind behind the chip design. He's a fantastic designer. I couldn't hope to be anywhere close to him in terms of design, but I'm lucky to have him as a collaborator. So he built this chip, and I had some small contribution. And it's a 45 spin code. A spin in this case is the SI variables. They refer to spin for historical reasons. And you can actually see that these spins are connected in some way. I'll talk about this later. You can put those on the board. The board can be connected to a PC. It all operates at room temperature at 10 milliwatts as opposed to some kilowatts, tens of kilowatts or something like this. Right? So the idea is, can you emulate this functionality on something like this, 10 milliwatts as opposed to kilowatts, at room temperature as opposed to millikilowatts? Okay. So this is the big picture idea. Let's become a little more concrete about it. All of this actually has its origins in magnetism. So Ising, as I mentioned, was a physicist, and they were looking at magnetic systems which have natural disorder. So as you know, when you have a magnetic system, you can have it oriented in one direction or another direction. That gives you the notion of a north pole or south pole, etc. And in some systems, magnetism can be disordered. It can interact, these disordered systems can interact with each other and create an ordered system. In this case, everything points in the same direction, but in some cases, you can have some pointing in the same direction, some in the opposite direction. This is often referred to as an Ising spin class. And again, I'm not a magneticist, but so I looked at this and I said, why the heck is this called a glass? So I spent a lot of time asking physicists this, and they didn't know the answer because they always took it for granted. So I went to my favorite source, Wikipedia, and it gave me the answer, and it says that, well, basically, quartz has a crystal structure that looks something like this. Regular glass has some imperfections and some disorder, and so this is, if you look at this disorder, it's almost like looking into a glass, and that's why it's called an Ising spin glass. I was involved in some work on spintronics about 10 years ago, I still am, and this was actually explored by a colleague, Supriya Datta at Purdue, in the context of magnetic tunnel junctions, and that's when I became acquainted with Ising computing. The idea is that, I think most of you know what an MRAM is. It's a magnetic memory with two states, depending on the magnetization. And the idea is that you can be in this state or in this state, and to switch, you pass a current, and you climb this barrier and get here. And there are ways of lowering this barrier, and when you lower it, you can actually have an almost sort of random movement from here to here. So this is the so-called super paramagnetism notion that has been used here, and that can be used to build e-sync machines. Here the status is the magnetization up or is the magnetization down. A quick primer on e-sync computation for dummies, which is me basically. So the idea is that it was kind of formulated by a guy named Ernst Ising. His advisor was Wilhelm Lenz, who actually came, Stefan can correct my pronunciation. So he came up with the problem, and he said, well, you've got this magnetized system, so try to find a stable state. He gave the 1D model to Ising, and Ising solved it. Turns out the 1D model is not particularly interesting because it's always stable. But when you look at the 2D model, you can have the so-called phase change where you go from a disordered to an ordered state, and that's really interesting. And that was solved by Lenz, but he gave the credit to Ising. So strictly it's called the Lenz-Ising or Ising-Lenz model. Graduate students here, if you want to look for an advisor, look for one like Lenz, who gives you all the credit for doing stuff that was invented by the advisor. Anyway, so when you look at this, there's this notion of interaction, there's a configuration probability that's given here, and this actually, for those of you looking at machine learning, this is basically a softmax function. So it looks at the landscape around, and it takes a softmax of that, and then it gives you a kind of an average weighted result. And then the H here is the interaction function known as the Hamiltonian, which is basically a quadratic function. Okay? So there's all of this sort of complex language, but ultimately what you're trying to do is minimize the quadratic function over space in some kind of a mean way. And when you think about this, if you're trying to minimize this function, what you try to do is to make sure that if j is positive, both of these are either +1 or both are -1, so the product is +1. If j is negative, then this negative j is positive, so you want this to be negative, so sigma I and sigma j will be +1 and -1, opposite states, etc. And then there's this extra term known as the phi term, which tries to promote lining up in one direction or another. So all of this, by the way, has links to the notion of simulated annealing, which we know very well. In fact, there's a Sherrington-Kirkpatrick model for this thing, where the Kirkpatrick is the same guy who did simulated annealing. So there is this notion of using temperature in here as well. So you can see the temperature here. There are other ways of using it as well. One way is you start with a known Hamiltonian with a known solution, which is called H0, and then you anneal it in some way to get from the initial Hamiltonian to the actual final Hamiltonian. So over time, this becomes 0, this becomes 1, etc. Now, the way we started with this was we looked at all of this, and eventually we said, we don't want to do this. We want to build a practical machine, something that works, something that will solve a combinatorial problem. Trying to emulate the physics exactly is extremely painful and probably unnecessary, because ultimately we want to solve problems, we don't want to necessarily emulate magnetism. So just a simulated annealing doesn't actually take a metal and melt it, etc., and cool it down slowly. The model that we have over here is inspired by the Ising model, but then it departs from it. Now, how does this go back to coupled oscillators? Remember that these were magnetic oscillators because magnetization can also oscillate according to this LLG model, for example. And so if you think about how you model this, there's actually a very nice paper by Jayajit Roy-Chaudhury and his student, which gives you sort of a generalized Adler equation. The Adler equation was for coupling between two oscillators. This is for coupling between n oscillators. And basically, it's a differential equation that says that if you solve this thing, that will give you the evolution of the oscillators. Now, notice that this is a continuous differential equation, which assumes that everything's varying continuously, works beautifully for sine waves. If you have something like this, there's a sort of a leap of faith that it's going to work for that as well, because it's not continuous, so what's a derivative going to be, etc. But actually, it does work out. It can actually be shown that it works. And in some kind of very recent work, we were actually able to show that when you look at these ring oscillators and you have discrete changes because one event propagates to another, it turns out that this is a continuous time approximation of a series of discrete events, and this Cij, which is the coupling function, can be correlated to something that you can characterize on a TSMC process, for example. So when this was done, these guys are spice simulation type of guys. I'm a timing analysis kind of guy. And so when I saw ring oscillators over here, I said, well, you don't really need to do all this. You can actually think about it as timing analysis. You have delays going through stages. You can think about these as discrete events. And you can actually use the principles of timing analysis to get pretty much the same thing and get it more accurately, because there are subtle effects that the continuous function doesn't capture. So the delay can be captured as a function of phase difference. This is an array of oscillators, and the oscillators are basically a bunch of inverters coupled in some way. You don't have to worry too much about the details of this, other than the fact that they are coupled structures. And when they are coupled, there's basically a region of transition. So if, for example, this is very far away from this transition, then the delay change is going to be something like this. If it's very far in this direction, that is, this is rising, this is falling, the delay change is going to be something else, and in between there's a transition. So as long as you characterize this, you're actually good, and then you can perform an event-driven analysis, and you can start from here using principles of timing analysis, and then you can actually propagate this thing. So for instance, if I have something that goes over here, and it interacts with other oscillators that are over here, then depending on the phase difference, I can have a shift of either this much, or this much, or this much, etc. So all of this can actually be quantified, and you can simulate how this thing works. And using this, you could actually look at the evolution of the ring oscillator periods. Notice that the ring oscillators will typically have different periods until they lock in step. Then they have the same period, and you can see that behavior here. Droid is the tool that we developed for doing this. And this actually shows you the evolution of the solution for 50 coupled ring oscillators. So let's look at the color code here. A phase difference of 0 or 2 pi, which means that it's in phase, is blue. Out of phase is red. So it starts off with, at time 0, with kind of random phases over here. Over time, these are snapshots over time, the phases sort of begin to change over here. And if I look here, for example, this starts with something like a purplish color, and then over time it evolves into red. So by the time you reach here, everything is either solid blue or solid red. And over time you can actually simulate this and see that this thing works. And in fact, this also correlates with hardware. And if we look at the cost function, the Hamiltonian cost function, this is the simulated value, this is chip measurement results, which actually tells you that the distribution of solutions is actually pretty similar. So, just to backtrack a little bit, what have we done so far? We've motivated the problem, we've talked about where it comes from, we've talked about the fact that these coupled oscillators can be built in CMOS. We've talked about the fact that there's a physics behind it, you can simulate it, and you can actually predict how it's going to behave. Let's now look at applications. We looked at number partitioning, but nobody's really interested in number partitioning, so what else can you do? The most natural formulation for E-sync solvers is the max cut problem, which is an NP-hard problem. And there's some maths that's shown over here, but basically if you're trying to minimize a Hamiltonian, which is a quadratic of this sort, then you can show through a series of steps that this is equivalent to minimizing this is equivalent to maximizing the cut size. Okay? And the math is actually not very easy. This is also available on Wikipedia if you want to look it up, or you can look it up later. But essentially the idea is you can feed this thing. These are the coupling strengths that you see here. You negate them and you feed them to the E-sync solver. Remember that each node is an oscillator. The negative of this weight is the coupling between the oscillators. You feed it to that and wait for it to reach its natural state, and you get the max cut. Now, this has been sort of done for a while, and people said, okay, nice, but how often am I going to use max cut in life? I'd like to do something more interesting as well. So, if you look at a 0-1 ILP, this is now beginning to get useful. So, I want to minimize C transpose X subject to some constraints. These are equality constraints. If there are inequalities, you add slack variables, except that Xi's have to be 0 or 1. Now we minimize an unconstrained Hamiltonian by replacing this with an unconstrained version. So the first part of it is the constraints over here, which is bi minus sji xi. You weight it with a factor a. You have the objective, which you also weight with something like this. So you basically take a weighted sum of this and a penalty function for violating the constraints, and you minimize this. And guess what? These are both quadratics. And quadratics fit very well into the Ising model, and therefore you can solve it, you can get the corresponding weights and solve this. Another example, integer knapsack. This becomes pretty useful in a number of contexts. You want to minimize the knapsack cost, which is a linear function of the choices, 0, 1 choices of weights, 0, 1 choices of cost, and the weight has to be less than some w. Again, this is a classical problem. This is linear, so you can again play the same trick over here, have the objective function and something like this. In this case, there's a kind of a gadget that you use to ensure that you enumerate all possible values of the objective function. It's not the only way of doing it, but it gives you a quadratic. There are other, notice that the interesting thing here is that when I look at this, I'm going to get quadratic terms with xi, xj interaction between all pairs of variables. And this is very important because this is something that you see in a number of contexts. There are all pair interactions between here, and this has been a major stumbling block in the past. There are cases where you don't have all pairs. For example, there's this important problem of factorizing the number 15, which was published over here. You can actually encode this number in terms of binary weighted digits, and you can write out a formulation of this sort. This is the Hamiltonian, minimize it, etc. If it's not 15, if it's a larger number, then this becomes a little more complex, and the problem becomes larger. Right? So in this case, you don't have all-to-all connections, but in many of these other cases, these useful problems, you have all-to-all interactions between the variables. And this becomes problematic because remember, we were looking at those 10 variables in a 2D plane, which means I can interact with my next door neighbor, but interacting with something that's far away is going to be hard. Okay? So this was sort of one of the problems over here. Okay. So now a bit of terminology. This is a term that's often used. It's referred to as QBO. It's nothing. It's basically a quadratic. Quadratic and constrained Boolean optimization. It means you minimize a quadratic, assuming that the variables have been Boolean. Okay. So this is just jargon that's used in the area. The Ising formulation typically doesn't use 0, 1 variables. It uses -1 plus 1 variables, and there's a very simple transformation that you can make over here, which gets you to something like this. So basically, these two are completely equivalent, but the language of Ising uses this, the language of QBO uses this thing over here. Very often, it's convenient to formulate problems in this way because we think more easily in terms of zeros and ones, and then go to this. Okay. Now, coming back to this all-to-all connection, we are not the first to propose these types of kind of hardware implementations. There's this work from Hitachi, which used an SRAM-based approach, and it created a 3D lattice of this sort. It was embedded in 2D space, and essentially, as you can see over here, you have nearest neighbor interactions in 3D. So if you have to have all-to-all interactions, say, between this and this, it gets a little complicated. There's some early work that we did which used a king's graph. A king's graph is basically the way a king moves in chess, right? It can move one square either way, horizontally, vertically, diagonally. And so you have connections of this sort. It's still a planar graph, and you still cannot have easy connections between this one and this one. There's D-Wave, this company in Canada, which has a graph of this sort. This was one of the earlier graphs called the Chimera graphs. They now have something called a Pegasus graph that looks something like this. This is still planar plus delta. What we would ideally want to get is this all-to-all connected topology, because then every variable can interact with every other variable and have a weight associated with that. Now, what is the problem with planarity? Let's say I want to embed K6, which is the complete graph of 6 vertices. If I want to embed it on the Chimera graph from D-Wave, then I need to replicate these spins over here, and I need to make sure that these are all very strongly connected. The problem is when I have to replicate these variables and connect them strongly, it gets weaker and weaker as I have more replications. In fact, if I just have a King's graph kind of topology, I can see that the embedding of this requires many replications of the first variable, and that's messy. So what we came up with was basically this idea where we could build an all-to-all connected system. So in fact, we built something which sounds small. It's got 59 spins. In the jargon of the field, we call them qubits. They're not actually qubits in the sense of quantum gates, but that's the jargon that's used. D-Wave claims 5,000 physical qubits, but if you look at them all-to-all, it's basically a linear connection versus a quadratic connection, so it's something like the square root of this physical so it's something like 47. So in CMOS, we're actually building something that's a little more complicated than this, with similar kind of coupling accuracy, 5 bits of coupling accuracy. Look at the density, the variation in the, here you need specialized fabrication, here you just kind of send it off to your favorite foundry. So the big challenge basically is connectivity over here, and this is a summary of kind of prior approaches. Some of these are Rydberg atom-based approaches that require atomic tweezers to place these things. I don't know how you're going to do that in the real world. These are superconducting. By the way, D-Wave is very successful, so I don't want to imply that it's not. They've been able to kind of deploy their things on real problems, and a lot of our approaches are also sort of inspired by their approach. So I don't want to sort of say bad things about them because they've been very inspiring in this area. But what we've been able to do is this all-to-all connection, which is CMOS at room temperature. So my colleague Chris Kim has been leading the chip tape-out effort, and he's been sending out a lot of chips over here. This is just a sample of chips that he sent out between January 2023 and May 2024. So you can see the students are very busy. This has been mounted on the board. It's referred to as SCOBY, and that's the coupled oscillator-based piecing machine. Okay, so remember I showed you this picture over here showing the notion of coupling over here. This was just a cartoon picture of how it has to be. In practice, you want every coupling to be equally strong. So if I have a coupling between oscillator I and oscillator J, and it's a coupling of 1, the location shouldn't matter. It should be exactly the same. So this requires very, very high levels of symmetry in the layout. This turns out to be a layout problem. So in fact, it turns out to be, even the topology of the structure turns out to be these coupled ring oscillators, some in this direction, some in the opposite vertical direction. The coupling goes through transmission gates in this particular version, and so the transmission gates basically emulate the resistors, and you can actually show that using this you get extremely high symmetry. The layout guys were very, very fussy about this, so everything had to be perfectly matched. I did some analog layout. The analog guys are nothing compared to these guys. These guys are extremely fussy. So I suggested, for example, that you could match resistances and capacitances even if you change layer, and they're like, no, we are not changing layers. We've got to keep it in the same layer to be perfectly matched. So this is the overall chip. Now the interesting thing is that if you look at the overall chip, the actual array is this thing. The rest of the chip is the overhead circuitry for this. But like any mixed signal system, this is the part that takes the most amount of effort to design. But once you have something like this, you can actually use all of this and you can program a system of this sort. So if I had to program, for example, Hamiltonian of this sort, then I could actually build it into this structure and program the weights associated with this. The improved model was a 59-spin all piecing solver. The one over here used these transmission gates, and the problem with transmission gates or resistors is that there's going to be static power dissipated in all of these. Even when you turn it, if this is connected here, if this is high and this is low, then there's going to be static power dissipated here. To avoid this thing, we actually came up with a scheme that used some gated transmission tri-state structures that eliminated the static power. And this is a 59-spin structure, and this is again operates at room temperature, oscillates at about 5 megahertz, etc. No static power, and the total power is 10 milliwatts as shown over here for the greatest amount of coupling. The actual structure looks something like this. I'll skip over the details of this, but you actually have a programmer's interface, and the programmer's interface allows you to specify the couplings between regions as shown using this. There are specific regions over here which are special oscillators. There's this notion of spin harmonic injection locking, which says that if you're kind of slightly off from being in phase or out of phase, you can nudge it with a very small signal which can kind of force it to lock in phase. So some of those details I'll skip over in this case. But that's the hardware that's being built. Okay, so now the last part of this is, I've got this hardware, I've got this theory, what am I going to do with it? How can I solve some real problems in the real world? And it turns out that working with this hardware, it's beautiful theory, but when the rubber meets the road, you have to work with the limitations of the hardware. So you say that you do everything to match all the strengths of the couplings, but it isn't actually exactly like that. You want to solve problems with, say, 100 or 200 variables, but you only have 59 spins that are available to you. How do you deal with all of that? So the other thing is that the solution basically is very probabilistic because it depends on noise, jitter, etc., none of which can be predicted. So you are required to repeat the solution. And that's not a problem if each solution is relatively fast and low power. You can repeat the solution multiple times. You can take the problem, repeat it multiple times, and then use the statistics to get the solution. So let's say you're trying to solve a satisfiability problem. You have a probability of P of achieving a solution each time. Even if the probability is, say, 10% or something like that, that's not too bad because over n attempts, which n can be relatively small, this is the probability that you'll never get a success. And so if you can do that, then you can actually get metrics like 99% accuracy. And there are standard metrics in this world that will predict the number of repeats that you need to perform to get, say, 99% accuracy. The limitations of the hardware are as follows. The first is limited hardware size. As I said, I want to solve, say, a 200 variable problem, but I only have 50 variables available to me. And in fact, it turns out that some of those variables are not actually available to me for reasons that I'll come to in a few minutes. So clearly, you need to partition, decompose the problem, and solve it. The other is your coupling weights have limited precision. So it's 5 bits, which means it's actually minus 14 to plus 14, so that's 29, not exactly 32, but close enough to 32 to claim 5 bits. But in a real problem, maybe you have 6.742 as your coupling weight. What are you going to do with that? Well, this is where you go to the real world and you say, well, okay, I'm going to sort of round it off. Maybe I don't get the optimal solution, but I get a pretty good solution, and if I can get it fast enough, I'm good. So you might perform some truncation. You might have wide ranges of weights. Some weights may be 0.1, some may be 92.4. So what are you going to do to fit that with the 32? You can scale it down, but then there are times when you have to figure out how to scale it, because sometimes you can just approximate the 92 as a 29, which is the maximum weight. Sometimes it's not a good idea, so you have to work with the range of weights that you have. So there's all this notion of scaling and truncation that you have to work with. Also, if you want higher weights, there are ways of actually doing that. So in this case, if you have something like this, you can have plus or minus 14 or 5-bit precision between these two. But if I clump these together, if I clump two of these, then it turns out that I can have plus or minus 56 because I can now have 4 couplers, each of them with plus or minus 14. So I can have plus or minus 56 as my maximum range of coupling. So I can play games of this sort, but this reduces the number of available spins by 1 every time I do this. So the big picture solution is something like this. You have a large combinatorial optimization problem. You have to partition it so it fits on the chip, feed it to the coupled oscillator array, read out the phase. By the way, input-output into a chip is also a very real problem. If you want to build a real system, then you have to deal with that. You get a solution for this, and then you iterate on this because you then go to the next partition and you keep going until you converge. So how has this worked? On the individual unit structure, we've looked at several problems: planar, maximal independent set, SAT, non-planar maximal independent set. Planar and non-planar just refers to the topology of the graph. So this shows the energy to solution and the time to solution. Ideally, you want to be on the bottom left, right? Low energy, fast time. And in fact, our solutions, which are shown by blue, which is barely readable, are over here, and competing solutions are up here across this range of problems. In fact, the problem becomes more interesting over here because for a planar graph, you don't have all-to-all coupling that's really required, but we still do better. In this case, this is our area of strength. Now, you can also kind of use another kind of degree of freedom over here. You can use parallelism. If each chip takes 10 milliwatts, you can use 1,000 of them and it's 10 watts. Big deal. You're competing with 20 kilowatts. So 10 watts is not a big deal. So in fact, you can take your larger problem, you can look at how you accelerate the solution, you can parallelize across repeats, you can parallelize across decompositions, all of the good stuff, and then you can use that. This, by the way, is not an AI-generated image. This is actual hardware that we built in order to show 4 Kobe chips that are shown here. And this is, even within a Kobe chip, we're actually building multiple Kobe cores. How do I map a problem? Let's look at the 3-SAT problem, for instance. This is a classical mapping. So let's consider 3-SAT with n variables and n clauses. So in this case, you can map it onto a maximal independent set problem. This is a classical mapping from Vazirani's textbook. And basically what it does is it takes each clause and it says, well, connect them using an edge over here. And connecting with it with an edge basically says, try not to use the same state for both of these. And what it says is, this way is, say, you just try to satisfy one of these. If you have to satisfy 2, it's okay, but try to do it with 1 first. More importantly, when I have x1 and x1 bar in 2 different clauses, I have an edge between them which says, make sure that these are different. So this adds a negative coupling which says don't use the same spin for this one and this one. And so you can create this mapping, and therefore if it's 3-SAT, every clause has 3 vertices. If I have n clauses, I have 3 spins in the problem. So notice that originally I had something like this. I had, in some sense, n plus m variables. So my 59 spins that I had that were available to me are actually getting eaten up by this factor of 3 over here. So I need to be more efficient. Fortunately, smarter people than us have done this before. There are a few formulations that are available out there. This is a formulation that we came up with. And if you compare these, then it turns out that, long story short, the Chancellor formulation, which is a standard formulation with n plus m spins, where n is the number of variables, m is the number of clauses, actually gives you the best performance in terms of achieving the all-SAT solution. It's not always better. The Nusslein solution is sometimes better, so that's the red and the blue. Sometimes blue is better than red, sometimes red is better than blue. But on average, Chancellor is the best. So if you have something like this, basically what you can do is you can kind of take your problem, decompose it. When you decompose it, you freeze all the spins that are outside here. When you freeze them, some of these values are going to be fixed to plus or minus 1 from the previous iteration. If this is fixed, then this value is constant. It's a constant, so it can be tossed out of the optimization problem. If both of these are fixed, then the coupling constant can be removed. If one of these is fixed, it becomes this term over here, like a field term. And if both of them are not fixed, then that's a coupling that you need to consider. So that basically creates your decomposed problem. And then even with this, it turns out that a lot of kind of variables get moved to this term over here because one of these is going to be fixed and it's going to be something like this. This coefficient is going to blow up. And there are again games that you can play over here because if you have a very high weight on some spins, a very high positive weight, then you want to make that minus 1 because you want to minimize the function and it's very incentivized to go to minus 1. So here are some early sort of runtime comparisons. This is all out of published work because we still have some work that's kind of coming out new pretty much every day as we speak. These are the StatLib benchmarks. They're relatively small, 20 variables, 91 clauses. With satisfiability, there's this so-called transition region. So satisfiability problems are easy if the number of clauses is very high or very low. If it's very high, it's very constrained. The number of solutions is not large. If it's very low, it's easy to satisfy. There's this middle region of where the ratio is something between 4.5 or 5.5, which is very hard, and this is sort of within that region. We compared it with 3 different solvers. This is the taboo solver, this is another stochastic solver, and this is the chip. And generally speaking, what we found was that we did sort of better than the taboo solver, worse than this other solver over here. But in terms of energy, there was basically no comparison because these were running on CPUs, this was running on the specialized chip. Now you might argue, well, why are you using Taboo? Why are you using WhatsApp? Why don't you use something like Chaff or Minisat or something of that sort? It's because we wanted to feel good about our results. No, the truth is that for these small problems, there's a lot of overhead associated with it. It's only when you go to larger problems that the benefit comes out. And so we have some very, very recent results on 200 variable SAT problems, where we are getting competitive with something like Minisat. And remember, again, all of these guys have been doing this for a few decades. We've been doing it for a couple of years. So our hope is that we're going to improve as we move forward. And there are many degrees of freedom. Like I said, with the decomposition, you can parallelize mercilessly. And as you parallelize, you can hopefully get kind of better efficiency. Having said that, we don't know what the future will hold. Maybe we'll be spectacularly successful. Maybe we'll be spectacular failures. So wish us luck. And at least this is sort of a very interesting direction, intellectually interesting, and it draws from all of the things I've learned at ISED. Timing, partitioning, optimization, etc. So to conclude, what we try to do is we work on this project that tries to build quantum-inspired piecing solvers. Notice that this is quantum-inspired because, for example, we are not doing any of the temperature annealing kind of stuff which is normally done in quantum annealing. And that's okay because we seem to be doing fine in terms of getting solutions. Repeating the problem and the presence of noise is actually a benefit that helps us. There are several challenges. We want to work on larger problems. We want to look at problems that work beyond the quadratic formulation. So we worked on K-SAT problems, 4-SAT, 5-SAT. Those are useful in many scenarios. And this ongoing work shows promise. We've been able to solve up to 7-SAT or so reasonably well. There are a lot of mundane issues when you're building hardware. So you have to deal with the file size. You need to bring data onto the chip. How do you do that? You need to worry about how you're going to get, for example, a connection to PCIe. How you're going to get AXI connection. So, for example, in many cases, instead of buying IP to do that, you just buy a small FPGA, and it comes with this IP on it, and it's relatively inexpensive. So, there are creative solutions like that that are very mundane, but they're required to make the things work correctly. In future, we see that our hope is in going for massively parallel solutions, and we've sort of looked at that direction. So this concludes the talk. I'd like to thank all of you for being patient. I'd like to thank all the students, and in particular my colleagues Triskim and Ulia Karkushchu, who've been very close collaborators to this effort, and for funding agencies that have supported us. Thank you.
Yeah, thank you so much, Professor. Now we have time for 2 questions. Okay. Good.
Thank you for a nice talk. Just a quick comment. When you use WhatsApp, you could also use Swedish hypothesis, right?
Yes.
So I think we tried it in 2010, and it works quite well.
Okay. Yeah, wait, you take that.
Time for, okay.
Igor, just one clarification. WhatsApp was used as a baseline for comparison for it. It's not a part of our approach.
So you can entangle all 58 bits.
Yeah.
So I assume that the chip size still increases parity if you add more bits. What do you see as a natural limit? What the number of bits that you might be able to do?
We've gone up to 70 or so, and there's, I think going much beyond that is going to be problematic because your coupling also weakens because you're taking a signal all along the ring oscillator. So the more stages you have, that's the number of coupling sites you have. So I would be very surprised if it went beyond 100. I think 50 to 70 is the optimal, and then decomposition is the solution. There are also other tricks that we've been trying. So instead of just working entirely within the space, the hardware actually has a greedy one-bit stochastic, one-bit gradient search algorithm built into it. And basically what it does is it reads the current solution, it flips chips one bit at a time, and it really takes a solution if it gets better. And we've been playing with the precision of the analog oscillator and this digital research, and we found that you can actually trade those off, and that helps sometimes.
So we are, one more question. Okay. We are kind of running out of time.
Your physical solution is a 2D solution. I know the parasitics are nasty, but to make the same chip in 3D dimension. In other words, the connections are 3D.
Let's put it this way. I'm working with a designer who's very, very, very conservative because he's working with 2 or 3 students building these chips, spending 10 or 20K for every fab. So I can understand where he's coming from. So if somebody gives us a giant infusion of money to build it in 3D, I'm happy to leave the effort.
So, yeah, thank you so much for such interesting talk. Let's give a big thank you to Professor Sachin.